Right now, while you're reading these words, something is happening that almost nobody on Earth knows about. A machine the size of a small car is moving through a part of the universe where no human being has ever looked, no probe has ever gone before, and no scientific model has ever been able to correctly predict what exists there. It is not a new spacecraft. It is not a product of modern engineering. It was built before the internet existed, before home computers existed, before most of the scientists currently studying its data were even born. It runs on roughly 4 watts of power. To put that in perspective, the small light inside your refrigerator uses more electricity than that. And this machine, this ancient, tiny, underpowered machine that was only ever supposed to last 5 years, is right now sending us information about the universe that is shaking the foundations of modern physics. The researchers who study its data are not using words like interesting or unexpected. They are using words like astonishing, baffling, and we were wrong. This is the story of Voyager 1. And here is the part the headlines are not telling you. It is not just what Voyager 1 found out there that should keep you up at night. It is what it found out there that directly affects the survival of life right here on Earth. It is what is happening to it right now in 2026 that nobody is talking about. And it is what is going to happen in a few months, a date already locked into the calendar, that will mark a moment no human civilization has ever reached before. Stay with me, because by the time this is over, you will never think about the night sky the same way again. I am your name, and this is your channel. Subscribe now if you want more stories like this, because we are just getting started. Let's go back to the beginning. September 5th, 1977. A rocket lifts off from Kennedy Space Center in Florida carrying a spacecraft called Voyager 1. The mission brief is simple and modest. Swing past Jupiter, swing past Saturn, take some photographs, collect some measurements, and then drift away into space and go quiet. The expected lifespan is 4 years, maybe 5. NASA plans to celebrate the mission's end sometime around 1981 or 1982. It would be a successful little trip, a nice postcard from the outer solar system, and then silence. What actually happened is one of the most extraordinary things in the history of science, and most people have no idea how extraordinary it actually is. Voyager 1 did not go quiet. It passed Jupiter in March of 1979 and sent back the first close-up images of that planet's surface that human eyes had ever seen. It passed Saturn in November of 1980 and kept going, accelerating as it went, using the gravitational pull of each planet like a slingshot to add more speed, more distance, more territory covered. By the time the 1980s ended, Voyager 1 had already traveled farther from Earth than any object humans had ever sent into space. And it was still transmitting, still sending its thin signal across the growing void, still collecting data, still functioning on hardware that modern engineers look at and shake their heads at in disbelief. Then in 2012, 35 years after it launched, something happened that made the entire story suddenly much bigger. Voyager 1 crossed the Heliopause. If you have never heard that word before, it is the single most important boundary in our entire cosmic neighborhood, and crossing it is the equivalent of stepping out of everything our civilization has ever called home. Here is how to picture it. The sun does not just provide heat and light. It constantly releases a stream of charged particles called the solar wind, and this wind blows outward in every direction, pushing against the surrounding space and forming a giant protective bubble around our entire solar system. That bubble contains every planet, every moon, every asteroid, every comet, every spacecraft we have ever launched, and every living thing that has ever existed. The outer edge of that bubble, the point where the solar wind finally runs out of energy and gets stopped by the pressure of interstellar space pressing inward from the other side, that edge is called the Heliopause. It is the actual physical boundary of our solar system. Everything inside it is ours. Everything outside it is something else entirely. And in 2012, Voyager 1 crossed through that boundary and came out the other side. It became the first object in human history to leave the solar system. Not a metaphor, not a technicality. The first physical thing our civilization has ever sent into the actual space between stars. And then it kept transmitting. Think about what that means. We have, right now, a live instrument sitting in interstellar space, not orbiting a planet, not floating in the outer solar system, not near the Heliopause. Actually, inside the dark, cold, ancient space that lies between star systems, a space that no scientist, no telescope, no model built from the ground has ever been able to directly observe from the inside. And it is sending us data about what that space is actually like. And what it is telling us is not what anyone expected. Here is where the first twist in the story arrives. For decades before Voyager 1 got there, scientists had built detailed mathematical models describing what interstellar space should look like. Not guesses. Serious, peer-reviewed, rigorously tested models built by some of the smartest physicists alive. And those models all told roughly the same story. Interstellar space, the plasma between the stars, should be relatively quiet, relatively smooth. A thin, cold, sparse environment where particles drift slowly and not much happens. A kind of cosmic waiting room between star systems. Voyager 1 walked into that waiting room and found it was actually a storm. Starting in 2017, the plasma wave instrument on board Voyager 1 began detecting something that nobody expected and nobody could immediately explain. A persistent, narrow band emission. A kind of faint but constant hum in the fabric of interstellar plasma that, according to every model built to describe this environment, simply should not be there in the way it is. Not a one-time burst, not a spike in the data that could be dismissed as a glitch. A continuous signal, year after year, stretching across a distance of over 900 million miles of interstellar space. To put that in perspective, the distance from the Earth to the Sun is 93 million miles. This emission has been detected across a stretch of space 10 times longer than the distance between our planet and our star. Scientists studying the data published in the peer-reviewed journal Nature Astronomy were clear in their conclusion. Interstellar space is not the quiet, uniform void that models described. It is turbulent. It has structure at every scale, from distances measurable in meters all the way up to distances measured in millions of miles. It is, in a physical sense, alive with motion and complexity that was completely invisible to us because we had never had a single instrument inside it before. Now, stop and sit with that for a second. Every model built to describe our universe beyond the solar system was built from the outside looking in, from a planet using telescopes and mathematics and theory. And now the first instrument we have ever actually put inside interstellar space is telling us that those models were missing something fundamental, that the universe beyond our solar system is more complex, more dynamic, more structured than we knew. But here is the part of this that stops being abstract and starts being personal. Because those discoveries about interstellar space do not stay out there. They reach back here. The same bubble that separates our solar system from this turbulent interstellar environment is the bubble that protects life on Earth. The heliopause is not just a boundary line on a scientific diagram. It is a shield. It deflects the most dangerous forms of cosmic radiation, the high-energy particles that stream in from distant exploded stars, from reaching the inner solar system at full strength. If that shield were significantly weaker or more unpredictable than our models suggest, the implications for biology on Earth would be enormous. And what Voyager 1 is telling us is that the interstellar environment pressing against that shield from the outside is more turbulent, more variable, and more energetic than any model has accounted for. We do not yet know exactly what that means for the long-term stability of the shield itself. But the fact that we now need to ask the question at all is itself a shift in how we understand our own vulnerability as a species. Now, the story gets stranger. Because before we get to what Voyager 1 found at the boundary itself, we need to talk about what happened in 2023. Because in 2023, Voyager 1 nearly died. For 5 months, the spacecraft continued to transmit a signal back to Earth. But what it was transmitting was gibberish, corrupted code, scrambled data that the engineers at NASA's Jet Propulsion Laboratory, after decades of experience reading everything the spacecraft had ever sent, could not decode. The instrument was still alive. The signal was still coming. But whatever it was trying to say had become unreadable. For a team that had been successfully operating this mission since 1977, this was unlike anything they had ever faced. The cause, when they finally identified it, was both simple and devastating. A single memory chip inside the spacecraft's flight data system had physically deteriorated after nearly 5 decades of constant exposure to cosmic radiation. One small piece of 1970s hardware, one chip measuring a fraction of an inch, had developed a fault that was corrupting the section of software responsible for formatting and transmitting scientific data. No alarm had gone off. No warning had been sent. The chip had just quietly failed after 46 years of non-stop operation in the harshest environment a human-made object has ever been placed in. In any normal engineering situation, you fix a broken component by going to where the component is and replacing it. In this situation, the component was 15 billion miles away, unreachable by any known form of transportation, with no repair mission possible in any time frame that would matter. The only available tools were radio signals traveling at the speed of light, and even those signals took 22 hours one way to reach the spacecraft. 22 hours just for the message to arrive, another 22 hours for any response to come back. Every single diagnostic step, every attempt to probe the problem, every test of a potential solution required a minimum wait of 44 hours to complete a single round of communication. Think about what that engineering process actually looked like from inside the control room. You look at a piece of data. You form a theory about what might be wrong. You write a set of instructions designed to test that theory. You transmit those instructions. You wait 22 hours. You receive whatever the spacecraft sends back. You analyze the response. You discover something slightly different from what you expected. You form a new theory. You write new instructions. You transmit them. You wait 22 hours again. You continue this process step by patient step for months. And every single moment of that process carries the knowledge that a single wrong instruction sent once across 15 billion miles of void could permanently end the mission with no recovery possible. The team at JPL worked through this for months, carefully, methodically, under a kind of pressure that most engineering situations never produce. And they succeeded. They figured out that the corrupted code could not be repaired, but it could be relocated. The affected portion of software was split into smaller sections and stored in different places in the spacecraft's available memory. Each section individually checked and rewritten to work correctly from its new location, then carefully reconnected to function as a whole. It was, in effect, brain surgery performed remotely through a 44-hour time delay on a machine nearly 50 years old, sitting 15 billion miles away. In mid-2024, Voyager 1 came back online and began transmitting clean, readable, complete scientific data again. And what it immediately resumed sending back was more evidence of those persistent, unexplained plasma oscillations in interstellar space. More measurements of the turbulent structure that the models had never predicted. The spacecraft that should have died in 1981 had come back from what could have been its final silence. And it came back with more things to tell us. But none of that, not the discovery, not the near death, not the recovery, prepared anyone for what Voyager 1 had actually found at the moment it crossed the Heliopause back in 2012. Because this is the part of the story that the scientific papers describe in language that stops feeling like physics and starts feeling like something else entirely. For decades, the models describing the Heliopause, the outer edge of our solar system, predicted what crossing it should feel like to an instrument moving through it. The solar wind on the inside gradually thinning out, the interstellar medium on the outside gradually becoming detectable. A slow, smooth transition from one environment to the other, a gradual blending at the edges, like the place where a river slowly meets the sea. That is not what Voyager 1 found. At the Heliopause, the particles were not thinning out calmly. They were moving at speeds approaching a significant fraction of the speed of light. They were slamming into each other at energies that generated temperatures approaching 30,000 degrees C. Not in the sun, not in any star, but at the outer edge of our own solar system, in what was supposed to be relatively cold, sparse transitional space. Some researchers have described this region as a wall of fire, and not fire as a metaphor, a genuine concentration of ultra-energetic charged particles forming a physical barrier at the boundary of everything we call home. And then the magnetic discovery. For decades, one of the foundational predictions about crossing the Heliopause was that the magnetic field environment would change dramatically. Inside the bubble, the sun's magnetic field. Outside the bubble, the completely separate magnetic field of the galaxy. Two distinct environments with distinct magnetic personalities separated cleanly at the boundary. Voyager 1 found something completely different. The magnetic fields on both sides of the Heliopause were, in ways that existing theory had not predicted, connected. The sun's magnetic field lines, carried outward by the solar wind and compressed at the boundary, were interacting with the galactic magnetic field outside in a process called magnetic reconnection, where field lines from different sources rearrange themselves and release energy in the process. The solar system and the galaxy surrounding it are not magnetically separate. They are magnetically linked. At the boundary between everything we know and everything we have not yet explored, there is a zone where energy is being exchanged between our home and the wider cosmos in ways that every model built before Voyager 1 crossed that boundary had simply not accounted for. This is not a footnote. This is not a minor correction to existing theory. If the relationship between the solar system and the interstellar environment is more dynamic, more connected, and more energetic than the models described, then our understanding of how the heliosphere protects Earth over geological timescales needs to be reconsidered from the beginning. Now, let's talk about what is happening right now in 2026, because the story is not over. It is, in fact, entering what may be its final chapter, and the timeline is tighter than most people realize. Earlier this year, NASA made a decision that nobody inside the mission wanted to make. The low-energy charged particle experiment, one of Voyager 1's scientific instruments that had been collecting data almost without interruption since the spacecraft launched in 1977, was switched off. Not because it stopped working. It was still working fine. It was shut off because Voyager 1 is running out of power, and there was no longer enough to keep it running. Voyager 1 gets its power from three devices called radioisotope thermoelectric generators. These are essentially containers of plutonium-238 that produce heat as the plutonium slowly decays. That heat is converted into electricity. At launch, these generators produced around 470 W of power. Today, nearly 49 years later, they produce roughly 250 W. They lose about 4 W every year. At some point in the early 2030s, the output will fall below the minimum level needed to run any remaining instrument at all, and Voyager 1 will go permanently silent. The team managing the spacecraft has known this was coming for years. Years ago, the scientists and engineers sat together and worked out a careful plan for which instruments to shut off, and in what order to squeeze as much scientific value as possible out of the dwindling power supply for as long as possible. Of the 10 scientific instrument packages Voyager 1 carried when it launched, 7 have already been turned off. The decisions about what to turn off and when are some of the hardest choices a scientific team ever has to make, because each instrument lost is a set of questions that will never be answered, and because there is no way to turn an instrument back on if you later decide you switched it off too early. But here's the twist that almost nobody outside the